Hello students, today we will try to use the concepts that we have learned yesterday to solve some problems. But before we start, let me revise what concepts we have learned yesterday. We know that for a linear circuit, for a linear symmetric circuits, the circuit would certainly look like this, where I had two circuits which has some common nodes and some supply. This is my circuit number 1 and this is my circuit number 2, and these are the inputs and these are the outputs, and I have some kind of connections that goes to the ground, and there is a particular important node which is known as, which I'm labeling it as VP here, which is called as common node. Okay, we know we can apply superposition theorem by considering the inputs V1 and Vin2 one at a time and analyze the circuit, since the circuit is basically a symmetrical circuit. Now we will apply two types of input signals to both Vin1 and Vin2 and see what happens to the output voltage at VO1 and VO2 as well as the common node voltage VP. So first we will see by applying anti-symmetric inputs across the input Vin1 and Vin2. Now what I really mean by the anti-symmetric input is that I'm just going to apply in the place of Vin1 as Vd by 2, and Vin2 is nothing but minus Vd by 2, and I'm just going to apply this table so that it becomes clear for us when we try to develop the concept. So this is nothing but a table with two entries. Okay, so as I stated, when we apply superposition theorem, I'm going to consider only one input at a time. So when Vin1 is basically equal to Vd by 2, I'm going to assume that the other node Vin by 2 is going to be 0 here. Now let us try to compute what are these values could be, like the VO1, VO2 and VO or VP. What will be the values at VO1, VO2 and VO and VP? Sorry, I'm keep skidding. To understand what would be the magnitude of these nodes, let me consider a resistive network which is going to be a linear circuit, and it has been made symmetric around the same node VP. Okay, so here what I have here is basically my Vin1 and here is my Vin2, and I have some resistance here. I assume that all of these resistances or four values of resistances are basically common or basically the same, and I have a node VP here, and the circuit is symmetric around about this particular node VP, which means that I have 2R at the top and 2R at the bottom, and it is symmetric over this node VP. Now I'm just going to label this one as circuit number 1 and the bottom one as the circuit number 2. Now just by applying this Vin1 with a voltage which we took right now as Vd by 2, and the other end of the node is connected to ground, let us assume that the values that I'm going to get out of this node VO1 and the node value VO2, let us assume that I'm going to get a value of VOA here, and here let us assume that I'm going to get a value of Vx here, and over the value of VO2 I'm going to get a value of VOB. Now clearly the value of VOA is pretty larger than the value of VOB, so we are going to utilize this concept when we do the other way around. Okay, now let us try to apply these values back to the previous table, and I'm just going to substitute those things. So just these values here. Okay, so now let us try to apply an anti-symmetric input to the other end of the terminal, that is nothing but my towards my Vin2, and then ground the node Vin1 here. Okay, so this would be my VD, sorry, I'm just writing wrongly. Okay, so just by applying BD by 2, I'm just going to remap all the magnitudes at these potentials or across these nodes. So now what happens is here, this would actually lead to a value which is equal to VOA, but with a negative sign because the input is a negative potential. So, and the next one, since it's somewhere at the midpoint of my residue network, this would lead to a value with a negative sign of Vx. And similarly, what I would get across VO1 node is basically minus of VOB here. And these values I'm just going to apply to the table back to the first page with VO1 right now being minus of VOB, and then minus of VOA, and over here it is minus of X. So now we can just apply the superposition theorem or just a simple addition here, and that would actually give us the following values across V in 1 and across V in 2 and VO1, which is nothing but VOA minus VOB, whereas here it would be VOB minus VOA here, and then when we add up these two nodes, this goes to 0. So clearly we can derive some intuition from the above results. So now I'm just going to write some of the intuitions that we have developed here. The first thing is, when an anti-symmetric input or applied to any linear symmetric circuit, the first thing that I know is the outputs are going to be antisymmetric. So that I can show it from by looking at VO1 and VO2. Clearly the magnitude of these two values are same, but the point is the polarities are totally opposite to each other, so which means that they are basically antisymmetric when I apply antisymmetric input. The second important result that I can derive is what happened to the common node that we had here, this node VP. So this node VP basically goes to ground. So that is the second observation that I'm going to make from the discussion. The nodes that are common to both the symmetric circuit goes to 0. So in general the common node goes to 0. Now let us see what happens to the node values when we apply symmetric inputs of same magnitude. Okay, so which means that I'm just going to apply V in 1 equals to V in 2, and that is basically equal to some common mode voltage here. So I'm just going to bring back this same table into my next page by writing down this V in 1, V in 2, VO1, VO2 and the node voltage VP, and there are two conditions here. So again I'm just going to apply superposition theorem, which means that I'm just going to apply each of these values that I've mentioned before one at a time, and then whereas the other value or the other input is going to be short to the ground. So let me try with this by applying VCM only to the input terminal V in 1, whereas the other terminal is going to go to 0. So now under such condition, I'm just going to look back to the same circuit and then make sure that I rig up the circuit with proper entries that I have made across the first row. So this time I have VCM here, whereas the other end of the node, which is V in 2, is basically shorted. Now what happens is I would get the magnitudes which is almost identical to, like, let us assume that these magnitudes are equal to VOA, and this was Vx, and this is going to be VOB. Now I'm just going to make those entries here, VOA across VO1 and VOB across VO2 and Vx across BP. Now let me go for the second condition where I apply the common mode input to the second input terminal, whereas the first one is being grounded. So due to which these two values has to be changed. So this goes to the ground, whereas I apply the common mode voltage across the V(2) terminal. So under such condition, what happens is I would have VO2 that is equal to VOA, and the node VP, which is exactly at the midpoint, will retain the same value, whereas this VO1 will change right now to VOB. And just rewriting those results back into my table would end up some kind of entry, something like this. So what happens is, like, when I apply the superposition theorem, there is nothing but the addition of these two entries that actually produces a value of VOA plus VOB across the output node 1, and the similar result, that is again VOA plus VOB across the output VO2, and the node VP carries VX plus VX. Again, deriving some intuition from the results, we can actually state that when a symmetric input signals are applied to a linear symmetric circuit, the nodes at the output will be symmetric, and when the values are same, we basically can short those nodes. Okay, so that is the one that I'm writing here. Short the nodes that have same potential. Now let us see how to apply these concepts from linear system to non-linear circuits, but yet symmetric circuit. When the small signal inputs are very small, we can assume that the circuit to be linear around the Q point. So based on that, the above results are basically valid for non-linear circuits like the diff amp or the differential pair, only for small incremental changes at their inputs. So this condition is really important when I want to apply the same concept that we have learned for a linear circuit to a nonlinear circuit like a differential pair. So now let us derive some important results by applying the above concepts upon differential amplifier. So I'm just going to draw the differential amplifier circuit here with a resistive load. Now let us define two type of input signals which are basically derived from this V(1) and V(2). The first signal is nothing but your differential input signal, which I can write it as V(1) minus V(2). And the second type of input signal is going to be the common mode signal or input common mode signal, which I can derive from those two input signals just by adding them and then dividing it by 2. Similarly, let us try to define the output signals which are again derived from these VO1s and VO2s. So again, with respect to the output, I have differential output, which I can take it as VO1 minus VO2, and again there is a common mode output signal which could be returned as a summation of VO1 and VO2 divided by 2. So thus, from 2 inputs and 2 output signals, we can derive 4 permutation expressions between the inputs and outputs. So I just go to the next page and try to explain that. So I have VOD upon VID. We know when we apply anti-symmetric input, the common node is driven to ground and the output becomes anti-symmetric. So this results in a simple common source amplifier with inputs one end being connected to VID by 2 and the other one terminal of V in 1 is connected to just minus VID. So which means that basically this particular point right now, which is termed as node VP, actually goes to the ground when I apply anti-symmetric input. So this is something like VID by 2 here, and this I'm going to apply minus VID by 2. Now so this particular circuit would actually get transformed into CS amplifier with VID by 2 at this input, and here is my VO1 and RD, and there is one more circuit with the gate being driven with the negative value of VID by 2, and the output is basically VO2. Now let us try to extract the value of VO1. As we know, the value of this would be GM RD VD by 2, and my VO2 would be equal to plus GM. If I take M1 here and M2 here, so obviously it would be GM1 for the top equation and GM2 for the bottom equation, and I have this VID by 2 here. Now since this numerator is basically a differential output, I have to perform VOD as the difference between VO1 and VO2. So that when I combine and do it, I would get a final expression which would be GM1, 2, assuming that both these GMs are same, into RD into VID, and this is my VOD expression. So from this expression I can get back to the final expression, which is going to be GM1, 2 times that of RD. So this is one of the permutation signal between the two type of inputs and outputs that I have, and clearly this will be the result. Now the next type of gain expression could be something like applying a common mode input and taking or observing the outputs differentially. As we know, for symmetrical input, the outputs are also symmetric. So what I'm trying to say is my VO1 would be exactly equal to VO2, and when we take the outputs differentially, that is VOD, which is nothing but VO1 minus VO2, then obviously this expression would lead to a 0 value, and because of that I can just apply the value as 0 for the second permutation signal. And there is again a third type of combination that I can apply, is by having a common mode output for a differential input signal. So again, we know that when I apply an antisymmetric input, the outputs will be antisymmetric, which means that I will have my VO1 would be exactly equal but opposite of phase, and when I try to compute the value of the common mode output voltage, it is nothing but is the average of VO1 plus VO2 divided by 2, and when we add these two values, it obviously goes to a value of 0, and that leads to having this expression being driven to 0 here. And the last combination is nothing but the common mode output voltage divided by the input common mode voltage. So this time probably we need some space to draw the circuit, but anyhow I'll try to recollect what we have stated before. For symmetric input, the outputs are all symmetric, and as I told, when the nodes have the same potential, we can short them. So thus this would lead to a kind of circuit where I have RD here, and then there are two transistors creating the differential pair, and I have some finite value of resistance RS, and the gates are basically driven with a common signal. So this would be my VICM, and these are the outputs, and this time the outputs are going to be symmetric here. Now, so when I state that the outputs are going to be symmetric, so this value will be exactly equal to this value, and because of that we can basically short these two nodes. So when we short these two nodes, what happens is I have two resistances RD and RD that goes in parallel, and that effective value could be returned as RD by 2. And here again, between this node and to the bottom node VP, there are two transistors that are connected in parallel, where the transistor M1 is identical to my transistor M2. So we know from VLSI design subject, the way that I can combine these two things would basically create a W by L factor, which would be twice, which means that considering that the value of M1 aspect ratio as W by L and the aspect ratio of my M2 as W by L, and when we try to combine these two transistors in parallel, would create twice that of the size. And over to the bottom, what I have here is the resistance RSS, and towards the input, which is a common mode input here. So clearly this circuit is the same as our common source amplifier with source degeneration resistance of RSS, and the gain from the input to the output is nothing but minus RD divided by 2, and there is a source resistance, so this is basically nothing but the drain resistance, and across the source I have a resistance RSS, and when I look through the source terminal, I have 1 upon GM 1, 2 as the resistance. So these two resistances actually goes in series, and due to which I have the total source resistance, which is 1 upon GM 1, 2 plus RSS, and this would be the fourth gain expression that I have. Now what happens when this value RSS goes to infinity? So clearly when this value goes to infinity, this VOCM divided by VICM will obviously goes to 0. So under ideal condition, there won't be any common mode gain, and that could be proved with this simple expression. Now let us do some analysis for the circuit shown below to help us to understand the above circuit. So you need to compute the differential gain for the circuit. So let me first try to draw the circuit. Yeah. So to compute the differential gain, that is the question that has been asked here. First, check whether the circuit is basically symmetric. So here in this case, since the value of W by L is not given, we can assume that all of these transistors are basically identical. That is, this M3 PMOS is identical to my M4 PMOS, and M1 NMOS is identical to my M2 NMOS. So clearly this particular picture gives us an intuition that this particular circuit is a symmetrical circuit. So now to compute the differential gain, we need an anti-symmetric input across our Vin. So my Vin is here, and I need an anti-symmetric input across these two terminals. We know when we apply an anti-symmetric input to a symmetrical circuit, what happens to this node, which is nothing but our node VP or common node, will actually be driven to ground, and this particular circuit could then be reduced down to a simple circuit or half of a circuit where I have M1 and M3 here, and that creates a diode connected, and here is my VO1, and at the input I clearly have half the VID or the differential input, and this circuit is basically a common source amplifier with a diode connected load. And we know what is the gain expression. So what is that? The capital GM of this particular circuit is basically approximated to GM1. It's not approximated, it's actually equal to GM1, and the output impedance when could be found just by shorting the input to the ground and then looking up would lead us to a particular value, which is GM3 prime in parallel with RO3, and when we look down through the drain terminal, the impedance would be RO1. So this top resistance goes in parallel with the bottom resistance, and that contributes to the total R out. So which would be GM3 prime parallel with RO3 in parallel with RO1. So clearly I can write the voltage at this particular output node to be just GM minus GM1 times the total R out, which would be GM3 prime RO3 and then RO1 into VD by 2. And the other output produces the same magnitude of VO1 but with opposite sign. So without any further analysis, I can write directly that this is going to be plus GM2 and then 1 upon GM4 parallel with RO4 parallel with RO2 into VID by 2. Now a differential gain is nothing but the output read differentially when the input is fed differentially, and clearly when we do the subtraction we'll get an expression which I can write it as GM1, 2 into 1 upon GM3, 4 and RO3, 4 and RO1, 2. Okay, so this is the differential gain for the circuit shown here. Clearly the result indicates that once one of the half circuit is drawn, we can find the gain just by applying, instead of VID by 2, I can just apply VID and then directly get this result. Okay, so I no need of considering this half here and then go back to next terminal and then considering the next half here and then doing all these stuffs. So just with, instead of applying VID by 2, I apply just VID to half of the circuit and directly compute the value. The value would be same. Now let us try to do one more problem, and this problem we have already done in the class, but I thought let me analyze it again. So the problem is, assume a differential pair with a resistive load where the differential pair has the W by L factors, which is 50 by 0.5, and then Kn dash, which is around 50 microampere per volt square, and the threshold voltage of 0.6 volt. And I'm just going to consider this lambda and gamma are not there. There is no channel modulation or no body effect is being considered for this computation. So the first question is, I think you need the circuit, so I just try to quickly make the circuit, and there is a resistance RSS and there is a current of 1 milliampere that flows through the resistance RSS, and this is my VN2, M2, M1 and VN1 and VO1, VO2 and then VDD. Yeah. So the first question is, what is the required input common mode for which the RSS sustains 0.5 volt across it? Okay, So the input common mode voltage is nothing but the gate potential here. So both these terminals are going to get shorted, and that's going to be fed with some common mode or a DC signal, which I'm taking it as a common mode input here. Now this VICM basically falls across two components. One is across the gate and source of VGS1 and the gate and source of VGS2, and the second part of the voltage will obviously appear across the resistance RSS. So which I can mathematically state that my VICM is basically VGS1, 2 plus the drop across the resistance RSS. And clearly from the question, the drop across RSS is going to be 0.5 volt. And what else we need to identify to compute the value of VICM is the value of VGS. Assume that the transistors are all biased in the saturation, so I can write the current equation of the transistor M1 and M2, which is going to be half K dash W by L VGS 1, 2 minus VT the whole square. And from this expression I can quickly derive the value of VGS1, and that would lead to the expression like this plus VT. Yeah. So since the tail current is 1 milliampere and the current through each of these branches would be obviously going to be half of it, which is nothing but 0.5 milliampere, and that would lead to a value of 1.47 volt. And so once I get the value of VGS, I can get the value of VICM, which is VGS2 plus 0.5, and that would lead to 1.547 volt. The second part of this question is to compute the value of drain resistance RD for a differential gain of 5. Since the circuit is symmetric, this circuit can be reduced down to a CS amplifier when we apply an anti-symmetric input, and based on that I can directly write the differential gain AD is nothing but minus GM1, 2 times that of RD. Now what was given here is like the value of differential gain was set to be 5, which is nothing but minus 5 here, and GM1, 2 is unknown, and what we have to find is the value of RD. Now you can just use any of the forms that we have discussed in the class to compute the value of GM, and what I got was it was 2.236 millisiemens. So from here on we can get the value of the drain resistance, and the value that I was getting after doing the computation was around 2.237 kilo ohm. And the third part of the question is, since the tail current source has a finite amount of resistance, there will be a non-zero VOCM divided by VICM, which I told at the end, if I guess you remember it. As I said, whenever the value of RSS is a finite one, if it is not equal to infinite, it is a finite quantity, then it is a non-zero term, which means that I have some gain from the input common mode to the output common mode. So based on that, let us try to compute the value of it and put the things in picture. So we know when we apply a symmetrical input to a linear system or linear symmetric circuit, the output will also be symmetric, and we have stated that the nodes that are having the same potential can be shorted together, and it's the same story like what I discussed. I'm just going to add this del term to this in order to represent that small change in the common mode, which is now visualized as a kind of AC component. That's it. Okay. Now out of all of these expressions or all of these terms that I have here, the term of RSS is unknown. There is the value of RSS is unknown, and that could be computed. Just we know across RSS I have 0.5 volt as a drop, and we know what is the current that is flowing, which is 1 milliampere, and that would lead to 500 ohm. So having all of these values known, we can get the value of this common mode signal as 1.545. okay, so this is actually the gain. Now what was given in this question was a change of 50. That is, I know the value of VICM is right now 50 millivolt, is higher than the previous value. So there is an increase in the value of input, and we know that this particular circuit is a type of common source amplifier, where the common source amplifier is basically a inverting amplifier. So when there is a rise at the input, it's obvious there will be a small reduction, or there will be a reduction at the output and that reduction quantity would be directly computed by shifting this term and multiply with the gain that we have got right now. So when we do that, we get the change in the output Q point as 1.545 into this 50 millivolt, and that would lead to a value of around 77 millivolt. There will be a shift at the output. Okay, so from the base, or from the Q point, when there is a rise of 50 millivolt, there is a reduction from the Q point by 77 millivolt, and that is actually the gain from input to the output, and that's how the new DC value has got shifted right now. Now let us switch back to our 4 equations that we have seen before. So out of those 4 equations, or those entire 4 set of equations, like I'm just going to number them so that I'm just going to refer those expressions with respect to those numbers. The whole of these results are applicable only when the circuit is symmetric. But what happens when there is a small mismatch between the components? Then this actually would lead us to something different. Like here I wrote that the value of differential output with respect to a common mode input was basically a 0 when the circuit is symmetric. But what happens when they are basically asymmetric? Then this term will never going to be a 0 term. So there will be a kind of non-zero term associated with it. And similarly, I can even prove whenever there is a kind of mismatch between any of the components, even this third expression will no longer be a 0 value. So in short, I can state that when the circuit becomes antisymmetric due to any mismatches, then the expression 2 and 3 will never be a 0 value. So it becomes a non-zero terms. To show, I'm going to take 2 individual cases. That is, the first assumption is, what if the value of RD1 is not equal to RD2, and the second case would be the value of GM1 is not equal to GM2. And then I'm just going to prove that the second as well as the third expression that I have shown before is going to be a non-zero value. First, let us assume that the drain resistance are different by assuming these values. That is, RD1 is equal to RT and RD2 is equal to RD with a mismatch whose value is del RD. Under such situation, the circuit becomes asymmetric. Now, when we apply a symmetric input, the output won't be asymmetric, which means that whenever I apply VICM, the output VO1 will not be equal to that of VO2. Proving that both 2 and 3 terms or 3 expressions would be a non-zero. So this is basically done in our textbook. Razavi has shown the derivation for showing how this expression 2 has become a non-zero term, and I will directly write the result here, because the derivation is already there in your textbook, which you can go through by yourself. So this is the term that I would end up. Okay. we know when the circuit is not symmetric, what happens when we apply a kind of anti-symmetric inputs. So in that case, as I stated before, for anti-symmetric input, and when we apply to an anti-symmetric circuit, the node that is common will not be driven to ground. But in this particular case, especially in this case, so I think the explanation would be fine if I try to draw the circuit first and then try to explain what I'm really trying to convince. So what I wanted to prove is this is my second term. I'm just going to show that the third term, which is VOCM divided by VID, is also going to be a non-zero, which is not there in your textbook, but still I thought let me give some intuition behind it. So clearly in this case I had a node VP, and because of this difference in the circuits across RD resistances, the circuit is no more symmetric. Okay, that is, as a whole picture they are not symmetric. And when we apply an anti-symmetric input across this Vn1, what happens is that, like, the assumption that we have made before, stating that the node Vp will be driven to ground, but this time this is not, or we cannot consider them to be a zero value. But is it true? Just look from the input perspective. So from the input, when I really look into the circuit, the input signal is basically being measured with reference to the ground, and with reference to that you could able to see that this entire part of the circuit, that is the bottom part of the circuit, is basically a symmetrical circuit. Okay, it becomes asymmetric when we try to observe the outputs, but otherwise with respect to the input the circuit is still symmetric, and due to which, under this condition, I can still assume that this node can be equal to 0. So what happens here is, like, so once I get to know this, I can apply this differential input, and when we apply the differential input, what we will get across output VO1 would be minus GM1 RD, and since it is symmetric, this VID will get equally divided across M1 and M2 gate to source. So what I have here is VID by 2 here, and whereas VO2 is basically defined as plus GM2 RD plus del RD times that of VID by 2. So now what we really want to measure is basically the common mode outputs. So now clearly the common mode VOCM is defined as the summation of these two terms divided by 2. Now it becomes pretty clear that when we try to add these two terms, the common terms that are here is basically the RDs would get cancelled out, and clearly I would get something that is del RD, and then VID by 2, and then GM1 comma 2. So here, since the transistors are symmetric, I could able to club them. Okay, and due to which I'm getting an expression which is ultimately showing me that this is going to be a non-zero. Okay, so I'm not sure about the exact result of this expression, but my intention is to show that there is a non-zero expression for it. Now again, let us go to the second condition, like the second case here. Writing my second expression, which is VOD by VICM, this becomes a non-zero, and the textbook has already shown you the value of it, like what is the exact value of this, which I'm going to write it. I'm not going to do any derivation here, just because it is already there in your textbook. I would advise you to just go through the textbook for this explanation. So clearly this particular term becomes non-zero just because there is a difference in the transconductance between GM1 and GM2, and that is the proof that is already been shown in your textbook. And now let me go for the third expression, which is written as VOCM divided by the VID. So this is my third expression, and this is going to be my second expression. For this particular term, the circuit is right now anti-symmetric, which means that I'm not dealing no more with the symmetric circuit as I stated before. So it is quite different from the previous condition we analyzed. So how exactly is that? So for which I'm just going to redraw the structure of my differential pair, and clearly because of some mismatch across my transistors, when I apply the common mode or when I apply the differential input between these two terminals of gates, what happens is I cannot equally divide them, or I cannot assume that this particular node goes to the ground. So this assumption right now becomes invalid just because a kind of unequal voltage that appears across the gate and source of M1 and M2, and that is because of the mismatch between the M1 and M2. So clearly I cannot have this node to be at the ground. We have analyzed such a condition in an exercise problem in class, which I'm going to do it briefly to show only the final method, but you can just always go back and recollect what I have done in the last lecture. So clearly this kind of structure, we can do it something like this. So whenever I look through or what I do is I just try to take off this and show it in a better way. So clearly there is a kind of current that flows through this node and loops back like this, and here is my VO2 and here is my VO1, and the current is looping like this. In order to measure what current that flows across these two source terminals, I can do it by looking across the source terminals of M1 and M2. Clearly when I look towards the source terminal of M1, I would have some kind of impedance which is nothing but 1 by GM1, and all the resistances like RO1 I'm going to consider as a very large value and then drop those values here. And when I look towards the source of my M2, there is a resistance whose value is 1 by GM2, and we know these two resistances will basically connect between the source and the gate terminal. So where the gate is right now is connected to my differential inputs. So I'm just going to take the gates of G1 and G2 and put them across the differential input VID. So clearly right now I want to measure what is the current. The current is basically I equals to the voltage, which is VID, across the resistances which are in series. So this is my series resistances. This current is going to loop around this resistance RD or through the output impedances. So now that I'm just going to try to write my output voltages, which is VO1 is nothing but the current that is flowing across the R out. Okay, so which is clearly is nothing but RD in parallel with RO1, and my VO2 could be written as, sorry, here I have to have a negative sign because the current is flowing towards the higher potential. So since I marked this current in this direction, so whereas for the case of VO2, the current is actually flowing away from this output, the highest potential, which I write it as I times RD in parallel with RO2. Now in this case I cannot really what I really wanted here is my VOCM, and we know that the value of VOCM is nothing but the summation of these two potentials and then divide by 2. But since because the currents are different through the transistor M1 and M2, the values of RO1 cannot be equal to RO2, so there is a kind of unequal values across these two output impedances, and due to which certainly there will be a difference here, or there will be a non-zero term. Even though they have opposite polarities because of the differential inputs, still the difference in value will appear here, and that leads to a kind of non-zero value across this VOCM divided by VID. Hope I've given enough explanation for the discussions that are not there in the textbook, and thank you.